The modern smartphone, a device that rests in billions of pockets and on countless nightstands, represents the peak of human engineering. A dense slab of glass and aluminium that serves as the primary interface between a biological entity and the digital universe. Yet, at the core of this miracle lies a fundamental paradox of physics and chemistry. Within the thin, pressurized confines of its casing is a substance so chemically aggressive that it occupies a unique position on the periodic table as both a savior of technology and a potential source of rapid thermal release. This substance is lithium, the lightest metal in the known universe, and an element characterized by a degree of chemical instability that borders on the volatile. The very properties that allow it to power a global network of communication also make it a material that cannot exist in its pure form in the open air without triggering a violent reaction. To understand the world today is to understand how a silver-white metal, soft enough to be sliced with a common kitchen knife and light enough to float on the surface of motor oil, became the indispensable engine of the 21st century. This exploration of the elements that define our era is part of an ongoing commitment to uncovering the hidden mechanics of reality. Subscribing to the channel and leaving a comment below helps ensure that these deep dives into the fabric of our technological world continue to reach a wider audience of curious minds. The physical reality of lithium is a departure from everything the human brain typically associates with the word metal. If one were to hold a bar of structural steel or a coin made of copper, the sensory input would confirm a dense, heavy, and rigid structure. Lithium defies these expectations entirely. Its density is approximately 0.534 grams per cubic centimeter, which is roughly half that of water. In practical terms, this means that if a standard shipping container were filled with lithium, it would weigh significantly less than if it were filled with seasoned oak. If placed in a container of hydrocarbon oil, the only way to store it safely, it does not sink to the bottom like a lead weight. It floats on the surface, bobbing like a piece of cork. This low density is a direct result of its atomic structure. As the third element in the periodic table, lithium possesses only 3 protons and 3 electrons. Its nucleus is tiny, and its electron cloud is sparse, meaning there is very little stuff packed into the space the atom occupies. This lightness is accompanied by a startling softness. In its pure, unoxidized state, lithium has the consistency of cold, refrigerated butter or a block of dense wax. A person could take a dull blade and press through a sample of lithium with minimal resistance. The moment the blade cleaves the metal, a brilliant, silver-white metallic luster is revealed, reflecting light with high efficiency. However, this beauty is fleeting. Within seconds, the shiny surface begins to tarnish, turning a dull grey and then a dark, charcoal black. This is not a choice made by the metal, but a rigorous thermodynamic necessity. Lithium is an alkali metal, and its electronic configuration is defined by a single, lonely electron in its outermost shell. In the language of atomic physics, this electron is loosely bound and eager to leave. The atom exists in a state of high potential energy, much like a tightly coiled spring held in place by a fragile latch. The moment oxygen or nitrogen molecules from the atmosphere collide with the surface of the metal, that latch breaks. The lithium atoms shed their outer electrons to bond with the air, releasing energy in the form of heat as they transition to a more stable, lower energy state. This chemical restlessness is what makes lithium a nervous element. While most metals are content to sit for centuries in a museum or a mine, lithium is constantly seeking a way to shed its excess energy. When it encounters H2O, the reaction is not merely a change in color, but a frantic display of physics. If a small sphere of lithium is dropped into a glass of water, it does not sink. It skims across the surface, propelled by the rapid generation of hydrogen gas. The metal reacts with the water molecules to form lithium hydroxide and hydrogen, a process that generates significant heat. This is an exothermic reaction, meaning it pumps energy out into the surroundings. If the piece of lithium is large enough, the heat can become so intense that it ignites the hydrogen gas, resulting in a characteristic crimson-red flame. This is the same reason why lithium batteries are treated with such extreme caution by aviation authorities.
If the thin plastic separator inside a battery, a membrane no thicker than a human hair, is breached, the lithium ions can rush through, creating a short circuit that leads to thermal runaway. This is a chain reaction where the heat from one failing cell triggers the next, much like a row of falling dominoes, until the entire pack is consumed in a fire that is notoriously difficult to extinguish because it provides its own fuel and heat. The reason humanity accepts this risk, placing such a volatile material inches from our faces and hearts, lies in the concept of energy density. To understand why lithium is the king of the modern world, one must compare it to the older generation of energy storage. For over a century, the lead-acid battery was the standard. These are the heavy, boxy units found under the hoods of internal combustion cars. They are reliable, but they are also incredibly inefficient in terms of weight. Lead is one of the heaviest stable elements, and using it to store energy is like trying to carry a gallon of water in a bucket made of solid gold. The container itself becomes the primary burden. If an engineer attempted to power a modern smartphone with a lead-acid battery, the resulting device would not fit in a pocket. It would be the size of a thick hardcover book and weigh several kilograms. The phone would be portable only in the sense that a brick is portable. Lithium solves this through its specific capacity. Because lithium is so light and so willing to give up its electron, it can store a vast amount of electrical potential in a very small mass.
In a lithium-ion battery, the metal doesn't even exist in its pure metallic "7" state. Instead, it exists as ions, atoms that have already given up that troublesome third electron. These ions move back and forth between two layers, typically a graphite anode and a metal oxide cathode. This process is often described using the __8__ analogy. When the phone is charging, the ions are pushed into the graphite layers, like people crowding into a stadium for a game. When the phone is being used, the ions "9" to move back to the more stable metal oxide layer, flowing through the internal structure of the battery like a river. As they move, the electrons they left behind are forced to take a detour through the phone's circuitry, powering the processor, the screen, and the speakers along the way. This internal movement is a masterpiece of precision engineering. The spaces between the atoms in the graphite are just large enough for the lithium ions to slide in, a process called intercalation. It is like parking thousands of cars in a multi-story garage where the floors are only millimeters apart. If the cars, the ions, were any larger, like the atoms of sodium or potassium, they would crack the structure of the garage. Because lithium is the smallest of all metal atoms, it can fit into these tight spaces without destroying the battery's internal architecture. This allows a lithium-ion battery to be charged and discharged thousands of times before the physical structure of the electrodes begins to degrade. The engineering required to keep this __10__ metal stable is immense. Every lithium battery is equipped with a battery management system, BMS, a dedicated computer chip that acts as a vigilant guardian. It monitors the voltage and temperature of the cells with microsecond precision. If the temperature rises above a certain threshold, typically around 60 degrees Celsius or 140 degrees Fahrenheit, the system may throttle the power or shut down the device entirely. This is because, at higher temperatures, the chemical stability of the liquid electrolyte inside the battery begins to break down. If the temperature hits 150 degrees Celsius, or 300 degrees Fahrenheit,
the battery enters the aforementioned thermal runaway.
At this point, the oxygen contained within the metal oxide cathode is released, feeding the fire, even if no external oxygen is present. It is a self-sustaining chemical furnace. Yet, despite this potential for chaos, lithium remains an ascetic. It does not require the massive, complex cooling systems that a nuclear reactor or a high-performance combustion engine might need on a relative scale. It sits quietly, a thin sliver of potential energy,
doing its work in total silence.
It is the invisible backbone of the mobile revolution. It is what allowed the laptop to transition from a heavy __quote_11__ machine in the 1980s to the paper-thin sheets of silicon and glass used today. It is the reason why a person can stand on a street corner in a remote city and access the entirety of human knowledge on a screen that glows with the energy provided by a few grams of a metal that was forged in the first minutes of the universe's existence. This is the everyday paradox of lithium. We have taken an element that is fundamentally incompatible with our oxygen-rich, water-heavy environment, and we have wrapped it in protective layers to make it the most intimate object in our lives. We sleep with it next to our heads. We trust it to keep our hearts beating in the form of pacemakers. We rely on it to bridge the gap between our physical selves and the digital ether. It is a high-wire act of chemistry,
a testament to the fact that the most transformative tools in human history are often the ones that are the hardest to tame. The smartphone is not just a piece of electronics. It is a controlled chemical reaction, a tiny piece of the Big Bang's leftovers, working tirelessly to hold the modern world together, one electron at a time. The presence of lithium on Earth is not merely a geological convenience, it is a cosmic anomaly that forces a reconsideration of the history of the universe itself. To trace the origins of a lithium atom is to look back past the formation of the sun, past the death of previous generations of stars, and into the first 3 minutes of existence. While most of the elements that constitute the human body and the world around it, carbon, oxygen, and iron, were forged in the nuclear furnaces of stars or the violent explosions of supernovae, lithium belongs to an elite and ancient group. It is one of the __quote_12__ elements created during Big Bang nucleosynthesis. In the immediate aftermath of the beginning of time, the universe was a soup of unimaginable density and heat, a state where the basic laws of physics were still settling into their current forms. As the universe expanded, the temperature dropped from trillions of degrees to a level where protons and neutrons could begin to cling to one another. The formation of an atom at this stage was a race against time and cooling. For a brief window of approximately 180 seconds, the entire universe acted as a single gargantuan nuclear reactor. In this period, protons, which are the nuclei of hydrogen, began to fuse together. This fusion is governed by a delicate balance of forces. At these temperatures, the electromagnetic force, which causes positively charged protons to repel each other like the matching poles of powerful magnets, was overcome by the sheer kinetic energy of their collisions. When they crashed together with enough speed, they entered the range of the strong nuclear force, which acts like a microscopic layer of incredibly strong industrial glue. Or __quote _13____. This allowed for the creation of helium and a tiny trace amount of lithium. However, as the universe continued its rapid expansion, the density of matter dropped so quickly that the __quote _14__ became too thin for larger atoms to form. The cosmic stove was turned off before it could cook anything heavier than lithium. This left the early universe composed of roughly 75% hydrogen
25% helium, and a billionth of a part of lithium. This makes lithium a biological and technological fossil, a direct physical link to the moment of creation. Yet, the story of lithium is defined by a deep irony. While the Big Bang was generous enough to create it, the stars that followed were designed to destroy it. In the heart of a star like the Sun, the temperature and pressure are so high that nuclear fusion becomes a sustained, self-perpetuating process. One might assume that this would lead to the production of more lithium, but the opposite is true. Lithium is exceptionally fragile at the nuclear level. To understand this fragility, one can compare it to a delicate piece of sugar glassware placed in a high-temperature kiln. While the kiln is necessary to forge strong ceramic plates, heavier elements like silicon or calcium, the intense heat simply melts or shatters the sugar glass. In the core of a star, at temperatures exceeding 2.5 million degrees Celsius, lithium nuclei are obliterated. When a lithium atom collides with a stray proton in these conditions, it does not grow heavier. It splits apart into two helium atoms. This __quote_15__ happens at temperatures far lower than those required to fuse hydrogen into helium. As a result, the very engines of the universe, the stars, act as giant _16, removing the element from the cosmos as they age. This creates what astronomers call the __quote_17__. When scientists use spectroscopy to analyze the light from the oldest, most ancient stars in the galaxy, they expect to see a specific signature of lithium left over from the Big Bang. Instead, they often find significantly less than the theoretical models of the Big Bang predict. The lithium seems to be missing. It is a cosmic detective story where the primary suspect is the star itself, which slowly circulates its outer layers into its hot core, effectively _18, its own primordial lithium over billions of years. Because stars are so efficient at destroying lithium, the fact that any of it exists on Earth at all requires an alternative explanation. If the __19__ of the universe are breaking it down,
Something else must be __quote_20__ it back into existence. This process is known as cosmic ray spallation. Space is not truly empty. It is filled with high-energy subatomic particles called cosmic rays, moving at nearly the speed of light. These particles are like microscopic bullets fired from the remnants of distant, exploded stars. When such a high-energy particle strikes a heavier atom, such as carbon or nitrogen, floating in the interstellar medium, the collision is so violent that it physically breaks the nucleus of the larger atom apart. It is a form of celestial __quote_21__, where a large stone is struck by a hammer to produce smaller flakes. Lithium, along with other light elements like boron and beryllium, is one of those flakes. This __quote_22__ in the cold vacuum of space is one of the few ways the universe can replenish its supply of lithium without immediately burning it up in a stellar core. The journey of lithium from the interstellar void to a lithium mine in the high deserts of the Andes or the salt flats of Australia is a testament to the chaotic formation of our solar system. Approximately 4.6 billion years ago, a massive cloud of gas and dust began to collapse under its own gravity, triggered perhaps by the shockwave of a nearby supernova. This cloud, the solar nebula, was a mixture of the _23 hydrogen and helium from the Big Bang and the _24 dust from dead stars, containing heavy elements like gold, iron, and the lithium produced by spallation. As the nebula spun and flattened into a disk, the heat of the forming sun pushed lighter gases, hydrogen and helium,
toward the outer reaches of the system, where they eventually formed gas giants like Jupiter and Saturn. Heavier, rocky materials stayed closer to the center, accreting into the terrestrial planets, Mercury, Venus, Earth, and Mars. Lithium, despite its atomic lightness, is chemically, quote, 25, quote, a term that literally means, quote, 26, quote. Even though it is the lightest metal, it does not like to be alone. It prefers to bind with oxygen and silica to form minerals. During the early molten stage of Earth's formation, when the entire planet was a roiling ball of liquid rock, the elements began a process of gravitational sorting. Heavy metals like iron and nickel sank to the center to form the core, much like lead shots sinking to the bottom of a bucket of water. Lighter elements, like the silicates that make up the crust, floated to the top, forming a thin, solid scum as the planet cooled. Lithium, because it bonds so readily with these lighter minerals, was carried upward. It concentrated in the Earth's crust rather than being locked away in the inaccessible core. This geological quote, 28 quote, is the only reason humans can reach it today. Even with this concentration, lithium remains elusive. It is not found in massive, concentrated veins like coal or iron. Instead, it is often found in pegmatites, igneous rocks that formed from the last, most water-rich dregs of cooling magma. As a massive body of underground magma cools, the elements that underscore quote, underscore 29, underscore, into the crystal structures of common minerals like quartz or feldspar get pushed into a leftover liquid. This liquid is like the concentrated syrup at the bottom of a bowl of fruit. It is packed with rare and quote, 30 elements. Eventually, this syrup cools and crystallizes into pegmatite veins, which are the primary source of hard rock lithium mining. Another, more common source of lithium on Earth is through the slow work of water and evaporation. Over millions of years, rainwater leaches tiny amounts of lithium out of volcanic rocks and carries it into basins with no outlet to the sea, such as the quote, 31 in South America, encompassing parts of Chile, Bolivia, and Argentina. In these high-altitude deserts, the sun evaporates the water, leaving behind a brine that is incredibly rich in dissolved salts. This brine is not like seawater. It is a dense metallic soup, sometimes 10 times more concentrated in minerals. Humans harvest this by pumping the brine into massive, turquoise evaporation ponds that cover hundreds of square kilometers. For months, the sun does the work of concentrating the lithium further until it can be chemically processed into lithium carbonate. When one considers the chain of events, the specific cooling rate of the Big Bang, the quote 32 of atoms in deep space by cosmic rays, the gravitational sorting of a molten Earth, and the precise evaporation of ancient lakes, the presence of a smartphone battery becomes a mathematical miracle. We are utilizing a material that the universe's primary energy sources, the stars, strive to destroy. We have reached into the crust of a tiny rocky planet to extract the remnants of the first 3 minutes of time. This cosmic accident is the only reason we have a metal light enough and energy dense enough to permit a world of portable electronics. If the Big Bang had cooled a fraction of a percent faster, or if the Earth had been slightly more effective at mixing its layers, the lithium age might never have happened. We would be tethered to walls by heavy copper wires, limited by the weight of lead or the inefficiency of other elements, forever denied the mobility that this ancient, fragile metal provides. The lithium in a modern battery is not just a component. It is a traveler from the dawn of time, having survived the destructive heat of stars and the chaotic assembly of planets to sit, silent and powerful, in the palm of a human hand. The transition of lithium from an obscure geological curiosity to a cornerstone of global industry
was not a linear path of scientific progress, but rather a fragmented history of medical experimentation and consumer marketing. For decades after its initial identification, this element existed on the periphery of human utility, a substance that seemed to possess strange properties but lacked a clear purpose. It was discovered in 1817 by the Swedish chemist Johann August Arfwedson while he was analyzing a mineral called petrolite. Arfwedson noticed that a significant portion of the mineral's mass was accounted for by an unknown alkali metal that was lighter than sodium or potassium.
He named it lithium, derived from the Greek word lithos, meaning stone, to signify its discovery within a mineral, unlike other common alkalis that were often found in plant matter. Yet, despite its identification, the metal remained a chemical ghost for nearly half a century. It was difficult to isolate in its pure state, and even more difficult to apply to the mechanical problems of the Industrial Revolution. It was not a structural metal like iron, nor was it a conductor of choice like copper. Instead, its first true integration into human society occurred within the internal chemistry of the human body. In the mid to late 19th century, lithium became the subject of a medical craze based on a fundamental misunderstanding of human biology. Physicians of the era were obsessed with the idea of lithic diathesis, a belief that an excess of uric acid in the blood was the root cause of a vast array of ailments, from gout and kidney stones to various forms of melancholy. Because lithium carbonate could dissolve uric acid crystals in a laboratory beaker, doctors theorized that it would do the same within the human bloodstream. This was an early attempt at chemical engineering within the body, treating the human circulatory system like a series of clogged pipes that required a specific solvent to clear the grit. Lithium was marketed as a miracle cure, leading to the popularization of lithia waters. Natural springs that contained even trace amounts of lithium became prestigious health resorts, and bottled lithia water was sold as a premium product for the elite. This was the first time the element entered the domestic sphere, not as a tool or a machine component, but as a biological cleaner. This obsession with the purported health benefits of lithium reached its cultural peak in the early 20th century with the birth of one of the world's most famous consumer brands. In 1929, just weeks before the catastrophic collapse of the American stock market, a businessman named C.L. Grigg launched a new soft drink originally titled _42. The beverage, which would eventually be renamed 7-Up, contained lithium citrate as its active marketing ingredient. The _43 in the name is often theorized to refer to the atomic mass of lithium, which is approximately 7 units. In an era of immense economic stress and social upheaval, the drink was marketed as a mood regulator. The lithium within the soda was intended to help the consumer feel, 44, and, 45, This was an age before the strict regulation of pharmaceuticals and consumer goods, allowing a powerful psychoactive metal to be sold as a refreshing accompaniment to a meal. For nearly 2 decades, until 1948, the public consumed lithium in their daily refreshments, unwittingly participating in a mass experiment in neurochemistry. The reason lithium had an effect on the human mood is rooted in the way the brain handles electrical signals. To understand this, one can view the brain as a complex telecommunications network where billions of neurons are constantly _46__ messages to one another. These messages are sent via a delicate exchange of ions, mostly sodium and potassium, moving across the membranes of brain cells. This process is like a series of gates opening and closing to allow a flow of water through a canal system. In certain psychiatric conditions, such as bipolar disorder, this _47_ becomes erratic. The gates may stay open too long, leading to a flood of activity known as mania, or they may fail to open at all, leading to the stagnant state of depression. Because lithium atoms are chemically similar to sodium atoms, but slightly smaller and more, quote, 48, quote, they can slip into the same biological, quote, 49, quote, that sodium uses. Once inside, however, lithium behaves differently. It acts like a, quote, 50, quote, on a high-speed engine, subtly slowing down the rate of signaling and stabilizing the internal pressure of the neurons. It doesn't shut the system down, it simply prevents it from oscillating between extreme highs and lows. The formal medical recognition of this stabilization occurred in 1948, the same year lithium was being removed from soft drinks due to growing safety concerns. An Australian psychiatrist named John Cade, working in a modest hospital with limited resources, began investigating the effects of lithium on patients with chronic mania. His experiments started with guinea pigs, where he noticed that injections of lithium carbonate made the animals remarkably calm and docile without putting them to sleep. When he moved to human trials, the results were transformative. Patients who had spent years in a state of agitated psychosis found a sense of clarity and stability. However, because lithium is a naturally occurring element and cannot be patented, large pharmaceutical companies had little incentive to market it. For several decades, lithium became a Cinderella drug, highly effective but overlooked and carrying a heavy social stigma. To be on lithium was to be marked as someone with a severe mental illness, a perception that pushed the element into the shadows of the clinical world. Throughout the 1950s and 1960s, lithium's identity was defined by the psychiatric ward. It was a tool of last resort, a salt that was difficult to dose correctly. Because the window between a therapeutic dose and a toxic dose is narrow, patients required constant blood monitoring. If the concentration became too high, it would begin to interfere with the kidneys and the thyroid gland, essentially clogging the biological machinery it was meant to tune. This era of lithium's history was one of quiet, often painful utility. It was a substance that saved lives, but at a significant cost to the patient's physical comfort, reinforcing its reputation as a, quote, 55 and, quote, 56 medicine, despite its atomic lightness. The pivot from the pharmacy to the electronics lab began as a result of the Cold War and the burgeoning space race. Engineers began to look at lithium not for its effect on the human brain, but for its physical properties as an anode. In the 1970s, during the global energy crisis, there was a desperate search for a way to store electricity more efficiently than the lead-acid batteries that had remained largely unchanged since the 19th century. The goal was to find a material that could hold a massive electrical charge in a lightweight package, the same requirement that makes lithium so effective in a modern smartphone. This research, led by figures like Stanley Whittingham and later John Goodenough, sought to move lithium out of the realm of, quote, 57 and into the realm of, quote, 58. They faced a monumental engineering challenge: how to harness a metal that, as previously noted, is prone to catching fire when exposed to the slightest moisture. The early prototypes were prone to exploding because they used pure metallic lithium, which would grow microscopic, needle-like structures called __quote_59__ during the charging process. These dendrites would eventually pierce the internal workings of the battery, causing a short circuit. The solution was to stop using lithium as a solid metal, and instead use it in its ionic form, the same form it takes in the human bloodstream. This realization bridged the gap between the history of medicine and the future of technology. The very properties that allowed lithium to slide into the __quote_60__ of a human neuron also allowed it to slide into the molecular layers of a battery's electrode. By the early 1990s, the first commercial lithium-ion batteries hit the market, and the transformation was complete. The __61_metal that had been a Victorian gout cure, a secret ingredient in a lemon-lime soda, and a stigmatized psychiatric medication, had been rebranded as the __62__ of the digital age. The element had been successfully moved from the internal environment of the human body to the external environment of human infrastructure. This historical journey reflects a broader pattern in human evolution. We often discover the most powerful forces in nature first through their effects on our own biology, before we learn to constrain and utilize them in our machines. Lithium's drama is the story of a substance that was always present, always potent, but required nearly 2 centuries of human trial, error, and cultural shifts to find its true place in the palm of our hands. The stigma of the psychiatric clinic has been replaced by the prestige of the high-tech laboratory, but the metal remains the same. A restless, ancient traveler, finally put to work in the service of a global civilization. The modern global infrastructure rests upon a foundation that is invisible to the naked eye, hidden within the sleek casings of portable electronics and the reinforced undercarriages of electric vehicles. If one were to remove lithium from the current technological equation, the results would be more than a simple inconvenience. It would represent a total collapse of the mobile age. To understand why this single element holds such a monopoly over the present, it is necessary to examine the concept of energy density through the lens of physical displacement. In the middle of the 20th century, a portable computer was a machine that required a specialized cart to move, largely because the energy required to power its vacuum tubes and early processors resided in massive lead-acid or nickel-cadmium cells. These older technologies are defined by a low ratio of energy to mass. A lead-acid battery is essentially a collection of heavy metal plates submerged in sulfuric acid. Because lead is so dense, it requires a massive amount of physical material to store a relatively small number of electrons. If a modern high-end smartphone were forced to operate on lead-acid technology, the battery required to keep the screen lit for a single day would weigh approximately 5 pounds, turning a pocket-sized device into a cumbersome weight that would strain the seams of any garment. Lithium provides the solution to this problem through a combination of atomic lightness and electrochemical potential. It possesses the highest power-to-weight ratio of any solid element. This is not a matter of chance, but a result of its position at the very beginning of the periodic table. Because a lithium atom has only 3 electrons, it is incredibly small. In the context of a battery, this size is a critical engineering advantage. A lithium-ion battery works on the principle of intercalation, which can be visualized as a process of sliding tiny marbles into the narrow gaps of a stacked structure. In a standard battery, the anode is typically made of graphite, which consists of many layers of carbon atoms arranged like the pages of a book. When the battery is charged, lithium ions are pushed between these pages. Because the lithium ion is so small, it can fit into these microscopic gaps without significantly warping or expanding the carbon structure. This allows for a very high density of energy storage within a very small volume. If one were to use a larger atom, such as sodium or potassium, the act of forcing those larger marbles between the layers would eventually cause the material to crack and crumble, leading to a rapid loss of battery life. The efficiency of this movement is what allows a modern smartphone to remain incredibly thin while processing billions of operations per second. The lithium ions act as a high-speed courier service, moving back and forth millions of times over the life of the device. This movement is facilitated by a liquid or gel electrolyte that allows the ions to flow while preventing the electrons from taking a shortcut through the center of the battery. This separation is vital. The electrons are forced to flow through the external circuit, the processor, the camera, the screen, to reach the other side. This is where the actual work of the digital world happens. The power that illuminates a pixel, or sends a signal to a cell tower, is literally the byproduct of a lithium atom's struggle to return to a state of lower energy. When this technology is scaled up from the size of a pocket to the size of a vehicle, the impact is even more transformative. For over a century, the electric car was a failed experiment, relegated to the role of a slow-moving golf cart or a niche delivery vehicle. The limitation was always the weight of the fuel. A gasoline engine is remarkably inefficient, losing about 70% of its energy to heat. But gasoline itself is incredibly energy-dense. To compete with the range of a combustion engine, an electric car needed a way to store massive amounts of electricity without becoming so heavy that it required most of its power just to move its own weight. Lithium-ion technology provided the breakthrough in the early 2000s. By bundling thousands of small lithium cells into a single pack, engineers were able to create a power source that could propel a 2-ton vehicle for hundreds of miles on a single charge. This shifted the perception of electric vehicles from environmental compromises to high-performance machines. The rapid acceleration seen in modern electric cars is a direct result of lithium's ability to discharge energy almost instantaneously. Unlike a combustion engine, which must wait for fuel to burn and pistons to move, a lithium battery can provide full torque to the electric motors the moment the circuit is closed. This same reliability and density make lithium indispensable in the field of modern medicine, specifically in the development of implantable devices. A cardiac pacemaker is a machine that must operate with absolute, flawless precision inside the human body, where the temperature remains a constant 98.6 degrees Fahrenheit and the environment is highly corrosive due to the presence of salts and H2O. Before the advent of lithium-based power, patients with pacemakers had to undergo invasive surgery every 2 or 3 years to replace the batteries. This was a significant risk and a major burden on the healthcare system. The introduction of the lithium-iodine battery changed the landscape of cardiology. These batteries have a remarkably low self-discharge rate, meaning they do not leak energy when they are not in use. They can sit inside a chest cavity, quietly providing the precise electrical pulses needed to regulate a human heart for 10 years or more without needing a replacement. The lithium in these devices is not the nervous and reactive metal of a smartphone battery, but a highly stable, solid-state configuration that prioritizes longevity and safety over rapid charging. The global economy has recognized this indispensability, leading to the rise of lithium as the white petroleum of the 21st century. The search for this element has become a matter of national security for the world's major powers. In the 1990s, lithium was primarily a specialty chemical used in glass and ceramics to reduce their melting temperature and increase their thermal shock resistance. Today, it is the primary focus of massive mining operations, from the high-altitude salt flats of the Andes to the hard rock mines of Western Australia. The process of extracting it is a feat of industrial-scale chemistry. In the salt flats, or salars, millions of gallons of lithium-rich brine are pumped into giant evaporation ponds. Over many months, the sun evaporates the water, leaving behind a concentrated slush of minerals. This slush is then treated with sodium carbonate to precipitate lithium carbonate, a white powdery salt that serves as the raw material for battery production. This industrial chain is incredibly sensitive to the purity of the material. Even a tiny amount of contamination, parts per billion of a different metal, can cause a battery to fail or, in extreme cases, catch fire. The manufacturing of lithium-ion cells takes place in gigafactories, environments that are cleaner than hospital operating rooms. The moisture in the air must be kept at a strictly controlled level, often below 1% relative humidity, because lithium's inherent reactivity with H2O is so high that even the water vapor in a human breath could degrade the quality of the electrodes during assembly. This level of precision is necessary to ensure that the nervous element remains a productive servant rather than a volatile hazard. As the world transitions away from fossil fuels, The role of lithium is expanding into the realm of the electrical grid itself. Renewable energy sources like wind and solar are intermittent. The sun does not shine at midnight, and the wind does not always blow when demand for electricity is at its peak. To solve this, engineers are building massive battery storage facilities, essentially shipping containers filled with thousands of lithium cells that can soak up excess energy during the day and release it at night. This turns lithium into a massive buffer for human civilization, smoothing out the fluctuations of the natural world to provide a steady, reliable flow of power. In this capacity, lithium is no longer just a component of a phone or a car. It is becoming a foundational part of the Earth's artificial nervous system. It is the silent regulator of our energy consumption, the invisible engine that allows a high-tech society to function in harmony with the erratic cycles of the planet. The journey from a trace element in the Big Bang to the primary regulator of human heartbeats and global energy grids is a testament to the transformative power of a single material, provided it is understood and contained with enough engineering rigor. The long-term legacy of human civilization is often written in the materials that endure long after the biological architects of those materials have vanished. Just as the Bronze Age and the Iron Age are defined by the metallic remnants found in the stratified layers of the Earth, the current era will likely be identified by future observers as the Lithium Age. Through the lens of deep time, the billions of lithium-ion batteries currently in circulation are more than just power sources. They are becoming a distinct geological layer, a chemical signature that will remain detectable for millions of years. When the glass and plastic of a modern smartphone eventually succumb to the slow pressure of tectonic movements and the corrosive influence of groundwater, the lithium within will not simply disappear. It will migrate into the surrounding soil and sediment, creating a concentrated geochemical anomaly that does not exist in nature. This element, which began its journey in the first moments of the Big Bang, is now being concentrated by human industry at a scale that fundamentally alters the chemical map of the planet. In the distant future, an archaeological analysis of the Earth's crust will reveal a sharp spike in the concentration of lithium, cobalt, and nickel within a very narrow band of sediment corresponding to the 21st century. This phenomenon is a form of technological fossilization. To understand how this works, one can look at the process of sedimentation as the Earth's way of keeping a diary. Every year, dust, volcanic ash, and organic matter settle in layers, like the pages of a massive stone-bound book. The industrial extraction and redistribution of lithium is equivalent to taking a rare pigment from a specific, isolated chapter of that book and smearing it across thousands of pages all at once. Naturally occurring lithium is usually locked away in hard rock pegmatites or dissolved in deep, ancient brines. By extracting it and placing it into billions of consumer devices, humanity is performing a massive redistribution of atomic matter. Future geologists will find pockets of lithium concentration in the ruins of ancient cities and landfills that are thousands of times more dense than the background levels found in the surrounding wilderness. This persistence is a result of the fundamental stability of the lithium ion itself. While the structures we build with lithium, the complex cathodes and sophisticated separators, will eventually break down, the lithium atoms are practically indestructible under normal planetary conditions. They may bond with oxygen to form lithium oxide or react with H2O to become lithium hydroxide, but the core nucleus of 3 protons remains intact. The nervous energy that makes metallic lithium so reactive is actually what ensures its longevity as a chemical marker. Because it is so willing to react, it quickly forms stable compounds that can survive for eons. In this sense, lithium acts as a silent and honest biographer of human mobility. It marks the moment when a biological species stopped relying on the slow, chemical energy of muscles or the heat of burning wood, and began to utilize the high-density electrical potential of the atomic world. The eventual fate of the lithium currently held in our hands is tied to the burgeoning science of the circular economy. As the surface deposits of lithium become more expensive and difficult to mine, the urban mine, the collective mass of discarded electronics, becomes the most valuable source of the element. The process of recycling a lithium-ion battery is a masterclass in restorative chemistry, but it is also a struggle against the laws of entropy. When a battery is manufactured, a great deal of energy is used to order the lithium ions into a specific high-energy arrangement. When that battery is used and eventually discarded, that order is lost. The recycling process is the chemical equivalent of trying to unmix a cake back into its original ingredients of flour, eggs, and sugar. It requires shredding the battery into a substance known as black mass, a dark, powdery mixture of carbon, lithium, cobalt, and nickel. This powder is then subjected to hydrometallurgy, a process where it is dissolved in powerful acids to separate the individual elements based on their specific chemical weights and affinities. The difficulty of this process ensures that much of the lithium used today will inevitably escape back into the environment. This leakage creates the geological footprint that will define our era. However, the move towards solid-state technology suggests that the way we use lithium will continue to evolve, even if the element itself remains irreplaceable. In a solid-state battery, the liquid electrolyte, the medium that allows the ions to travel, is replaced by a solid ceramic or polymer. This allows for even higher energy densities and eliminates the risk of the thermal runaway, fires that occur at 150 degrees Celsius. It represents a transition from a liquid and volatile technology to a solid and more controlled one. Yet, even in these advanced systems, the protagonist remains the lithium ion. Its small size and high electrical potential are simply too efficient to be replaced by heavier, more sluggish elements like sodium. As human civilization potentially expands beyond the confines of Earth, lithium will travel with it. The same properties that make it ideal for a smartphone make it essential for life support systems in the vacuum of space. Lithium hydroxide is used in space capsules to scrub carbon dioxide from the air, a process where the lithium chemically binds with the CO2 to prevent it from reaching toxic levels for the crew. In this application, lithium is not a power source, but a biological filter, a chemical guardian that allows humans to survive in environments where they do not belong. This dual role, as both the engine of our digital lives and the protector of our biological ones, solidifies lithium's status as the most important minor element in the human story. Through the millions of years that follow the eventual decline of our current technological era, the lithium we have moved will remain as a testament to a period of unprecedented transition. Long after the electrical grids have gone cold and the satellites have tumbled back into the atmosphere, the concentrated pockets of lithium in the Earth's crust will stand as a chemical monument. It will tell the story of a species that learned to harvest the remnants of the Big Bang to create a world without wires. It will reflect a time when the lightest metal in the universe was used to carry the heaviest burden of human communication and memory. In the grand cycle of the cosmos, lithium is a rare and precious gift. It was born in the intense heat of the early universe, survived the destructive interior of the stars, and was concentrated by the tectonic and solar forces of a small, rocky planet. Humanity has simply taken its turn with this restless element, pulling it from the silence of the salt flats and the darkness of the mines to make the world glow with the light of a billion screens. Eventually, through the slow work of erosion and subduction, these lithium atoms will be pulled back into the depths of the Earth, where they will once again become part of the molten mantle. They may remain there for billions of years until the sun expands into a red giant and the Earth itself is consumed. returning its constituent atoms to the stellar forge. In that final act of thermal release, the lithium will be destroyed by the same nuclear processes that once threatened it in the hearts of the first stars. Until then, it remains our most faithful companion, a sliver of the ancient past that makes the modern future possible, resting quietly in the machines that define the human experience. It is the silent, silver-white thread that connects the beginning of time to the palm of the hand, an element that has moved from the void of space to the center of our hearts, both literally in our pacemakers and figuratively in our constant connection to the world.